This video is on the inverse trig functions for integration. The three integrals involving inverse trig functions are the ones that we have here. Those are the only ones that we'll be using. However, make sure that you also have out your derivatives with inverse trig functions for the examples we're about to do. For this first example, we're going to take a squared to be 9, so that our a is 3. We're going to take u squared to be x squared, so that our u is x, and our du is just dx. When we rewrite this, we get the integral of du over the square root of a squared minus u squared, which simplifies to the inverse of sine of u over a. U in this case is x over a, which is 3, plus c. For part B, a squared is 5, so our a is equal to the square root of 5. U squared is equal to 4x squared, so that u is equal to 2x. Our du would be 2 dx, divide by 2 on both sides. Rewrite it, pull out the constant, so half of du over a squared plus u squared simplifies to 1/2 times 1 over a, which is the square root of 5, inverse of tan of u over a, and plus c. Here we let a squared be 9, so that a is 3. U squared is equal to x squared, so that u is x. Du is dx. When we rewrite this, we get du over u, square root of u squared minus a squared, which then simplifies to 1/3 the inverse of secant of the absolute value of x over 3 plus c. For this example, we're going to use u substitution. So we're going to set u equal to the inverse of sine. The derivative of the inverse of sine is 1 over the square root of 1 minus x squared dx. So when we rewrite this, we get the integral of u du, which then simplifies to u squared over 2 plus c. Replace u, so we have the inverse of sine squared over 2 plus c, and that would be our answer for this one. We have more u substitution here, so u is equal to tan inverse of x. Derivative of that, looking at our previous set of notes, is 1 over 1 plus x squared dx. We rewrite it as u squared du, integrate it, becomes u cubed over 3 plus c, and replace u, so we get tan inverse cubed over 3 plus c. For this next example, it's going to get a little tricky, so let me try to explain this as best as I can. We take a squared to be 16, so a is equal to 4. We let u squared equal to x to the 4th, which then allows u to be x squared. Du would be 2x dx. We're going to divide here by 2x, because in our original problem we only have dx by itself. When we rewrite this, it'll be, I'm going to split it up into two fractions, du over 2x times 1 over x square root of u squared minus a squared. The reason I did this is so that I can multiply these two, take out the constant first, so 1/2, multiply the two fractions, so I have du over x squared square root of u squared minus a squared, but I know that x squared is the same thing as u, so I'm going to replace that, so 1/2 du over u square root of u squared minus a squared, and that looks like one of my formulas. Let me erase this so I can make some space. So then this becomes 1/2 times 1 over a, the inverse of secant of the absolute value of x squared over 4 plus c. For this next example, we're going to evaluate using long division. All I did was take my denominator and rewrite it. Manipulating the addition won't change anything. Now, I want an x squared, but I have an x squared, so what do I multiply this x squared to get this x squared? Well, I multiply it by 1, so then that'll give me x squared. 1 times 1 will give me 1, and then I subtract them, so x squared minus x squared cancel. 0, which I have nothing inside, minus 1 gives me a negative 1. So my new integral becomes the integral of 1 minus 1 over 1 plus x squared dx. By integrating, we end up, since we're integrating in terms of x, we have x minus, this here looks exactly like our integrals involving inverse trig functions, which is on the front of this page. So that's the same as saying the inverse of tan of x plus c. For these next two examples, we're going to be completing the square. And completing the square is a concept that you learned in Algebra 2, but in case you don't remember, I've included some key points here. We would call these the side job, which was taking our b value, dividing it by 2, and squaring it. So what we do essentially is we take x squared plus bx plus the side job plus c, and then minus the side job. So we're not really adding or subtracting anything, but we need this in order to be able to factor our equation. So if we look at the example on part A, I'm going to complete the square, so it'll be the integral of dx over x squared plus 12x plus half of b in this case is 12, 12 divided by 2 is 6, squared would give me 36, plus, and I'm going to put that inside of a set of parentheses, plus c, which is 37, and then minus 36, which was our side job. Inside my parentheses, when I factor this out, not factor, when I, factoring, it becomes x plus 6 squared, and on the outside, I have a plus 1. Well, here, we can set the variable portion to be u squared will be x plus 6 squared, so then that'll give us u to be x plus 6, and our a squared to be 1, which will give us an a of 1, and this would look like dx over u squared plus a squared, which, looking at the front of this page, is the same thing as tan inverse of u, which is x plus 6 plus c. I erased example A to make some space for example B. On this left side, I have already completed the square, simply because it's a bit tricky and I didn't want to run past the 10-minute limit, but I'll post up the solutions on Edmodo as to how I completed that square. And then now, given that I have a squared and I have u squared, I know that my answer would be the inverse of sine of 3x plus 1 over the square root of 5 plus c. this is the end of the integration of inverse trig functions. I hope this video has helped you a bit with this, and I shall see you soon.